Look up at the night sky. What do you see? Stars, planets, maybe a distant galaxy if you're lucky. But beyond that glittering curtain lies something far more mysterious. Vast regions of the universe we can't explore. Places where the laws of physics, as we know them, seem to break down. These enigmatic corners of space defy our understanding, teasing us with questions we can't yet answer. What lurks in the voids between galaxies? What happens inside a black hole's crushing depths? Why does 95% of the universe remain hidden from us, made of dark matter and dark energy we can't see or touch? The truth is, for all our telescopes and probes, humanity has barely scratched the surface of the cosmos. Think about that for a moment. We've sent robots to Mars, photographed the edges of our solar system, and even captured the glow of galaxies billions of light years away. Yet some parts of the universe might forever remain out of reach, locked behind barriers we can't cross, not because of distance alone, but because the very fabric of reality behaves differently there. Take the cosmic horizon, for example. Even if we built a ship that could travel at the speed of light, we'd never reach it. The universe is expanding faster than we could chase it, leaving whole regions eternally isolated. And then there are places like the centers of black holes, where gravity warps space-time so severely that our physics textbooks might as well be blank pages. This isn't just about scientific curiosity, it's about the limits of human ambition. Every time we push the boundaries of exploration, the universe reminds us how much we don't know. But that's what makes these mysteries so thrilling. They're not just gaps in our knowledge, they're invitations to dream bigger, to question deeper. So today, we're setting off on a journey to map the unmappable, to explore 25 of the most bewildering regions in the cosmos, places that challenge everything we think we understand. From the eerie silence of the Boötes Void to the violent chaos inside quasars, these are the frontiers that might forever remain beyond our grasp. Buckle up. The universe is about to show you how strange it truly gets. Hidden behind the veil of our own galaxy lies one of the most perplexing gravitational mysteries in the cosmos, the Great Attractor. Imagine an invisible hand tugging at everything around it, pulling entire galaxies toward some unseen point in space. That's exactly what's happening 650 million light-years away, in a direction obscured by the dense stars and dust of the Milky Way's zone of avoidance. This region is so crowded with cosmic material that telescopes struggle to pierce through it, leaving scientists to study the Great Attractor indirectly by observing how it warps the motion of galaxies around it. The story of its discovery reads like a cosmic detective tale. Back in the 1970s, astronomers noticed something strange. Galaxies in our local universe weren't just drifting apart due to the expansion of space. Instead, they were all streaming toward the same point, as if caught in a slow-motion river current. The culprit, a gravitational force so immense it could only come from a structure with the mass of tens of thousands of Milky Ways. But what is it? The leading theory suggests a supercluster of galaxies, a colossal knot of matter hidden behind the zone of avoidance. Yet even that might not explain the full strength of its pull. Some researchers speculate dark matter plays a key role, with an unseen concentration of this mysterious substance amplifying the effect. Here's what makes the Great Attractor so fascinating. It's not just pulling us, it's part of something even bigger. Recent observations reveal our entire galactic neighborhood, including the Great Attractor itself, is being drawn toward an unfathomably massive structure nicknamed the Shapley supercluster, over 600 million light-years beyond it. It's like peeling back layers of a cosmic onion, each discovery revealing deeper, larger forces at work. This raises a mind-bending question. Are we seeing the true scale of the universe's structure, or is there always another, greater attractor waiting to be found? What's certain is that the Great Attractor humbles us. For all our technology, a fundamental part of our cosmic landscape remains hidden in plain sight. reminding us how much we still have to learn about the forces shaping the universe. And as new telescopes peer through the zone of avoidance with infrared and radio eyes, we might finally glimpse what's been pulling the strings all along. Now, let's venture into one of the most unsettling expanses in the known universe, a place so empty it's earned the nickname, the Great Nothing. The Boötes Void stretches over 330 million light-years of near-total darkness, a gaping hole in the cosmic web where galaxies should be crowding together but instead barely appear at all. Picture throwing a handful of sand across a football field. That's roughly the density of galaxies in this region compared to the rest of the universe. Astronomers first stumbled upon this ghostly expanse in the 1980s while mapping galaxy distributions, expecting to find the usual bustling neighborhoods of stars. What they found instead was a void so vast and empty it seemed to break the rules of cosmic structure itself. Why does this emptiness rattle scientists? Because according to our best models of the universe's evolution, regions this large simply shouldn't exist. The Big Bang's afterglow shows a remarkably even distribution of matter in the early cosmos, and over billions of years, gravity should have pulled galaxies into a relatively uniform cosmic web. Yet the Boötes Void throws a wrench into that picture. One theory suggests it's a fossil from the universe's infancy, a bubble inflated to monstrous proportions during the split-second chaos of cosmic inflation. Another proposes it's the scar of an unfathomably ancient collision between our universe and another, a speculative idea from multiverse theory. Then there's the wild-card hypothesis. Could advanced civilizations have somehow engineered this emptiness, harnessing the energy of entire galaxies and leaving behind a deserted footprint? While that idea veers into science fiction, it underscores how little we truly understand about this void. Here's what makes the Boötes Void even more intriguing. The few galaxies trapped inside it aren't like the ones we know. Dubbed wallflowers, these isolated star systems show bizarre traits. Some are strangely young, others unusually quiet, as if the void itself has altered their evolution. It's as if the universe conducted an experiment here, placing galaxies in extreme isolation to see how they'd develop, and the implications ripple outward. If voids like this exist, could there be others, even larger and emptier, lurking undetected in the cosmic shadows? Yet for all its mystery, the Boötes Void isn't just a cosmic oddity. It's a reminder of how much we rely on assumptions. Every time we point our telescopes at the night sky, we're subconsciously expecting the universe to follow patterns we recognize. But places like this force us to confront an uncomfortable truth. The cosmos might not play by our rules. As future telescopes probe deeper into the void's secrets, one thing is certain: the Great Nothing still has a lot to teach us. Rising like ghostly pillars from the heart of our galaxy, the Fermi Bubbles are cosmic behemoths that defy simple explanation. These twin lobes of superheated gas and radiation stretch 25,000 light-years above and below the Milky Way's disk, so vast that if our eyes could see gamma rays, they'd dominate the night sky like a colossal hourglass of light. Discovered in 2010 by NASA, a Fermi Gamma Ray Space Telescope, these structures initially went unnoticed because they don't emit visible light. Instead, they hum with high-energy gamma radiation, a whisper from some cataclysmic event that rocked our galaxy in the distant past. What could create such enormous energetic formations? The prime suspect sits at the very center of the Milky Way, Sagittarius, a star, the supermassive black hole anchoring our galaxy. Astronomers suspect that 6 million years ago, this cosmic monster awoke from its slumber in a violent feeding frenzy, devouring nearby gas and stars. The resulting explosion of energy may have blasted material outward at nearly the speed of light, inflating these bubbles like cosmic balloons. But here's the puzzle: the edges of the Fermi bubbles are razor-sharp, as if contained by some invisible force. That's unexpected for an ancient explosion which should have diffused over millions of years. Some theories suggest magnetic fields are corralling the particles, while others propose ongoing energy injections from the black hole's faint but persistent activity. The mystery deepens when we examine what's inside these bubbles. They're filled with particles moving at mind-bending speeds, generating gamma rays as they collide with interstellar gas. Yet the exact mechanism powering this radiation remains elusive. Normally, we'd expect such energy to come from known processes like supernova shocks or pulsar winds, but the Fermi bubbles operate on a scale that dwarfs these everyday cosmic events. Even stranger, their shape doesn't match the messy aftermath of a single explosion. Instead, they hint at a more organized process, almost as if the galaxy itself has a hidden energy regulation system we've yet to understand. Perhaps most intriguing is what the bubbles imply about our galaxy's hidden life cycle. We often think of the Milky Way as relatively quiet compared to active galaxies with violent cores, but the Fermi bubbles suggest our home has a volatile past and possibly an active future. If Sagittarius, a star, can erupt with enough force to sculpt structures this large, what else lies dormant in our galactic center? As new telescopes map the bubble's faintest emissions, we might uncover clues about the Milky Way's secret history of upheavals written in gamma rays across the sky. For now, these glowing enigmas stand as a reminder. Even our home galaxy still keeps astonishing secrets. We might think of our cosmic neighborhood as ordinary, just another unremarkable corner of the universe, but what if we're actually floating in a gigantic void? The KBC Void, named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, is an immense bubble-like region of space where galaxies are sparser than expected, stretching over 2 billion light-years across. And here's the twist: our Milky Way sits right at its heart. This discovery throws a wrench into one of cosmology's bedrock assumptions, the cosmological principle, which states that on large enough scales, the universe should look roughly the same no matter where you are. If we're truly inside one of the biggest underdense regions ever observed, it forces us to reconsider just how average our viewpoint really is. What makes the KBC Void so unsettling isn't just its size, it's the way it warps our measurements of the universe. Take the Hubble constant, the rate at which the cosmos is expanding. Scientists have long struggled with conflicting values for this number, depending on whether they use nearby supernova or the faint glow of the Big Bang. But if we're inside a void, that could explain the discrepancy. Less matter here means weaker gravity, allowing space around us to expand faster than in denser regions. It's like standing in a valley and trying to guess the world's average elevation. You'd get a very different answer than someone perched on a mountaintop. The controversy lies in whether this void is a statistical fluke or a fundamental challenge to our models. Some researchers argue it's just a rare but expected fluctuation in the cosmic web, while others see it as evidence that the universe's structure might be far more irregular than we thought. There's even a wilder possibility. Could this void be the imprint of an ancient collision with another universe, a fossil from the multiverse? While that remains speculative, the mere existence of the KBC Void forces us to confront an uncomfortable truth. We might not be the unbiased observers we assumed. Our entire understanding of cosmic expansion, dark energy, and the universe's fate could be skewed by the fact that we're peering out from inside a cosmic anomaly. Yet for all its mysteries, the KBC Void also offers an opportunity. If confirmed, studying it could give us unprecedented insights into how voids evolve and influence their surroundings. Galaxies inside underdense regions might age differently, with slower star formation due to their isolated environments. And if voids like this are more common than we thought, they could act as cosmic magnifying glasses, subtly bending light in ways that reveal hidden matter. One thing's certain: the universe keeps reminding us that perspective is everything. Even as we map the farthest reaches of space, we're still learning how much our own backyard might be shaping the view. Among the faint whispers of the Big Bang's afterglow, one anomaly stands out like a cosmic bruise: the Eridanus supervoid. This enormous cold spot in the cosmic microwave background, or CMB, spans over 1 billion light-years, registering temperatures noticeably cooler than its surroundings. When scientists first detected it in 2004, it defied expectations. The CMB should be nearly uniform, bearing only minor fluctuations from the primordial universe. Yet here was a region so cold some theories struggled to explain it. Is it a shadow cast by one of the largest voids ever discovered, or could it be evidence of something even more extraordinary, a collision with another universe? The most straightforward explanation ties the cold spot to a corresponding underdensity in the distribution of galaxies, a supervoid. The logic seems sound. As light travels through a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. But there's a problem. The Eridanus supervoid would need to be impossibly vast and empty to account for the temperature drop we observe. Even the largest known voids only cause minor CMB distortions, nothing as dramatic as this frigid patch. Some researchers argue we might be seeing the combined effect of multiple aligned voids, while others suggest our understanding of how voids interact with light needs reevaluation. Then there's the more radical possibility that this cold spot isn't just a void but a fingerprint from beyond our universe. The multiverse theory, still speculative but mathematically plausible, suggests our cosmos might have bumped against another bubble universe in the distant past. Such a collision could have left an imprint in the CMB, a kind of cosmic birthmark. While this idea electrifies the imagination, it's far from proven. Skeptics point out that instrumental errors or statistical flukes could still explain the anomaly. After all, the CMB is a tapestry woven with countless fluctuations. Finding one extreme outlier might not be as unlikely as it seems. What makes the Eridanus supervoid particularly compelling is how it forces us to question our tools as much as our theories. Could our telescopes be missing subtle structures that would explain the temperature drop? Or are we glimpsing the limits of current physics, where the rules we've relied on no longer apply? Future sky surveys, especially those mapping galaxy distributions in 3 dimensions, might finally resolve the debate. Until then, this enigmatic cold spot remains a tantalizing puzzle, one that reminds us the universe always has another surprise waiting. Deep in the fabric of space, something impossible is happening. Entire clusters of galaxies are streaming in the same direction at breakneck speeds, as if pulled by an invisible force we can't see or explain. Astronomers call it the dark flow, and it's one of the most unsettling cosmic mysteries ever uncovered. Picture this: hundreds of massive galaxy clusters, each weighing trillions of suns, all drifting toward a single point beyond the edge of our observable universe. It's not the gentle motion of cosmic expansion, it's a directed march, like iron filings drawn to a magnet we can't locate. The discovery came in 2008, when scientists studying the cosmic microwave background noticed something bizarre. Galaxy clusters weren't just moving apart as space expanded. They showed a peculiar velocity that couldn't be explained by the distribution of matter we've mapped. Even stranger, this motion pointed toward a region of space with no known superclusters or massive structures, nothing that should exert such a gravitational pull. The only explanation: something enormous lurks beyond our cosmic horizon, so distant its light hasn't had time to reach us in the 13.8 billion years since the Big Bang. Skeptics argue the dark flow might be an artifact of measurement errors or incomplete data. But multiple studies, including ones using NAS, a Wilkinson microwave anisotropy probe, and Planck satellite, have detected this motion independently. If it's real, the implications rewrite our understanding of the universe's structure. One radical theory suggests the dark flow is evidence of a gravitational tug from a neighboring universe, a parallel cosmos brushing against ours in the multiverse. Others propose it could be the echo of a pre-Big Bang structure, a relic from whatever existed before our universe began. Imagine a cosmic tree with roots extending beyond what we can observe, its unseen mass still influencing everything within our reach. Then there's the spine-tingling possibility that we're seeing the fingerprints of something even stranger, a region where space-time itself is fundamentally different. Some models of quantum gravity allow for exotic structures beyond our horizon that warp the fabric of reality in ways we can't yet describe. Whatever's causing the dark flow, it's clear our universe is playing by rules we've only begun to glimpse. Until we develop telescopes capable of peering beyond the observable universe's edge, this enigma will remain a haunting reminder. The cosmos is far stranger and far larger than we ever imagined. Turn your gaze toward the center of our galaxy, and you'll find more than just stars. You'll hit an invisible wall. The zone of avoidance isn't some cosmic barrier or force field. It's a sprawling curtain of dust and gas so thick it swallows light whole. Stretching along the Milky Way's equator, this region obscures nearly 20% of the sky, blotting out entire galaxies that might lie just beyond our sight. Imagine trying to study a cityscape through a snowstorm, except this storm is made of interstellar soot, stretching tens of thousands of light years. For centuries, astronomers treated this zone as a blind spot, marking star charts with literal voids where data should have been. But today, we're learning to see through the fog. The challenge isn't just about blocked starlight, it's about distortion. Visible wavelengths get absorbed or scattered by dust particles, while infrared and radio waves slip through more easily. That's why modern telescopes like the Spitzer Space Telescope and the Atacama Large Millimeter Array have turned their attention here, peeling back the layers with wavelengths our eyes can't see. And what they've found is staggering: hundreds of hidden galaxies, some grouped into massive clusters previously unknown to science. One of the most jaw-dropping discoveries. The Vela supercluster, a sprawling network of galaxies weighing in at 100 quadrillion suns, lurking just beyond the dust. Without the zone of avoidance, we might have spotted it decades earlier. But here's where it gets even stranger. Some of these hidden galaxies aren't just obscured, they're behaving differently. A few appear unusually isolated, drifting through the void without the usual entourage of dwarf galaxies. Others show signs of rapid star formation, as if the dust itself is triggering stellar births. There's even evidence of entire clusters warping spacetime behind the curtain, their gravity bending light in ways we're only beginning to map. These anomalies raise a tantalizing question. Is the zone of avoidance merely hiding galaxies, or could it be actively shaping them? What keeps astronomers up at night is the possibility that we're missing something far bigger. If entire superclusters can hide in plain sight, what else might be lurking in the shadows? Some theorists speculate that the zone could conceal primordial black holes, rogue planets, or even exotic matter we've yet to classify. Others wonder if it's the perfect hiding spot for advanced civilizations after all. A dense dust cloud would mask artificial radio signals as effectively as starlight. While that remains speculative, one thing's certain: the zone of avoidance isn't empty. It's a frontier challenging us to invent new ways of seeing. Every photon that slips through the dust carries a secret, and with each technological leap, we pull another piece of the hidden universe into the light. At the very heart of our galaxy, a silent monster lurks: Sagittarius, a star, a supermassive black hole with the weight of 4 million suns crushed into a space smaller than our solar system. For years, astronomers assumed it was relatively quiet, a dormant giant slowly sipping on wisps of gas, but recent observations reveal a far more volatile story. This cosmic behemoth occasionally erupts with violent flares, blasting out X-rays and gamma rays with no clear trigger. Imagine a sleeping dragon that sometimes, without warning, breathes fire into the void. One of the most baffling mysteries surrounding Sagittarius, a star, is the missing stars paradox. According to our best models, the galactic center should be packed with thousands of stars orbiting close to the black hole. Yet when astronomers look, they find a surprising emptiness. Where did they go? One theory suggests the black hole's immense gravity shredded them long ago, scattering their remains into unseen debris. Another proposes that the extreme environment near the black hole prevents stars from forming in the first place, leaving a cosmic dead zone. But there's a wilder possibility. What if something else is hiding them? Some researchers speculate that dark matter or even exotic physics could be at work, warping our observations in ways we don't yet understand. The Event Horizon Telescope's groundbreaking image of Sagittarius, a star in 2022, gave us our first direct glimpse of its shadow, a dark silhouette ringed by swirling light. But instead of solving mysteries, it deepened them. The black hole's accretion disk, the glowing ring of superheated matter spiraling into it, appears strangely lopsided with brighter patches that don't match predictions. Even more puzzling are the sudden flares that sometimes ignite in this disk, launching jets of energy thousands of light years into space. These eruptions don't align with any known feeding cycles, leaving scientists scrambling for explanations. Could magnetic fields be twisting in unexpected ways, or is the black hole interacting with yet undetected objects nearby? Then there's the enigma of G objects, clumps of gas and dust near Sagittarius, a star that behave like stars, surviving tidal forces that should tear them apart. These cosmic anomalies seem to defy physics, appearing and disappearing without warning. Some astronomers wonder if they're the remnants of failed stars, while others suggest they could be something entirely new, a form of matter or energy we've never classified. Every time we think we're close to understanding our galaxy's heart, it throws another curveball. Perhaps the most humbling realization is how little we know about the environment surrounding Sagittarius, a star. The laws of physics as we understand them start to break down in its extreme gravitational grip, warping time and space beyond recognition. Future telescopes, like the upcoming Laser Interferometer Space Antenna, might detect the faint ripples of merging black holes or uncover hidden objects orbiting just beyond the event horizon. Until then, Sagittarius, a star, remains a riddle wrapped in a paradox, a reminder that even in our own galactic backyard, the universe still holds its greatest secrets close. Stretching across nearly half the night sky like a cosmic scar, the Magellanic Stream is one of the Milky Way's most dramatic conquests. This colossal ribbon of hydrogen gas, spanning over 600,000 light-years, traces the violent history of two dwarf galaxies, the Large and Small Magellanic Clouds, as they're slowly devoured by our galaxy's gravity. But here's the puzzle. When astronomers compare the stream to computer simulations, the numbers don't add up. The gas is far more massive than it should be, and its complex structure defies expectations, hinting at forces we've yet to uncover. For decades, scientists assumed the stream formed simply like saltwater taffy being pulled apart. As the Magellanic Clouds orbit the Milky Way, our galaxy's gravity should strip away their gas, leaving behind a trail. Yet detailed observations reveal something far richer. The stream isn't a single filament but a braided tapestry, with multiple strands twisting around each other. Some sections glow brighter, dense with ionized gas, while others appear almost hollow. Even more startling, the entire structure weighs at least 1.5 billion suns, 3 times heavier than models predicted. Where did all this extra mass come from? One clue lies in the cloud's tumultuous past. Radio telescopes have detected faint echoes of star formation along the stream, suggesting bursts of supernova long ago might have blown gas outward, puffing it up like cosmic cotton candy. But the plot thickens. Recent studies show parts of the stream moving against the expected flow, as if tugged by invisible hands. This has led to 2 radical possibilities. First, dark matter might be playing puppeteer. The Magellanic Clouds are thought to be swaddled in halos of this mysterious substance, and their gravitational dance could be stirring the stream in unpredictable ways. Second, there might be another player in this drama. Astronomers have spotted a dim, previously unnoticed galaxy trailing the clouds, dubbed the dark Milky Way due to its lack of stars. Could this ghostly neighbor be warping the stream with its gravity? The Magellanic Stream isn't just a relic of destruction, it's a laboratory. As gas from the stream plummets into the Milky Way, it ignites new stars, offering a rare chance to study galactic cannibalism in action. But its greatest gift might be hidden in its chemistry. Unlike the Milky Way's pristine hydrogen, the stream's gas is peppered with heavy elements forged in the hearts of ancient stars. By mapping these metallic fingerprints, we could reconstruct the Magellanic Cloud's entire life history, tracing stellar births and deaths across billions of years. What makes this cosmic river so mesmerizing is how it challenges our vision of galactic interactions. We often imagine gravity as a sculptor, shaping orderly orbits and predictable structures. Yet the Magellanic Stream, with its tangled strands, rogue motions, and unexplained mass, reveals a far wilder universe where chaos and beauty intertwine. Every new telescope trained on it peels back another layer, proving even our closest cosmic neighbors still guard astonishing secrets. Some voids in the cosmos shout their strangeness with sheer size, but others whisper mysteries through their peculiar emptiness. Nestled near the southern constellation Fornax lies one such enigma, the Fornax Void, a region spanning 60 million light-years where galaxies are scattered like distant campfires in a vast desert. At first glance, it might seem unremarkable compared to giants like the Boötes Void, but what makes Fornax fascinating isn't its scale. It's the way this void defies expectations, housing fewer galaxies than predicted, yet somehow nurturing strange pockets of star formation where none should exist. Most cosmic voids follow a predictable pattern. Matter flees their centers, leaving behind near-total emptiness as galaxies cluster along the void's outer edges. But Fornax plays by different rules. While its core is eerily sparse, astronomers have spotted isolated galaxies deep inside it, floating like lone ships in an ocean of darkness. Even stranger, some of these galaxies show vigorous star birth, a phenomenon usually triggered by collisions or dense gas clouds, neither of which should exist in such an underdense region. It's like finding a lush oasis in the middle of a wasteland, fed by springs we can't see. So how did Fornax form? One theory points to its unusual location, sandwiched between the sprawling Fornax and Eridanus galaxy clusters. These massive neighbors may have acted like cosmic vacuum cleaners, pulling matter away over billions of years and leaving behind a drained region. But that doesn't fully explain the void's odd galaxy distribution. Another idea involves dark energy, the mysterious force accelerating the universe's expansion. Some models suggest dark energy behaves unevenly, creating pockets where its push is stronger, effectively clearing out regions like Fornax faster than elsewhere. The real puzzle lies in those star-forming galaxies. If voids are meant to be galactic deserts, why are these flickers of life here? One possibility is that they're survivors, ancient galaxies that formed when the universe was denser and somehow avoided being pulled into clusters. Their star formation might be fueled by hidden reservoirs of cold gas, remnants from an era before the void expanded. Alternatively, their activity could be a cosmic illusion. Galaxies might appear isolated when in fact they're connected by faint bridges of dark matter, funneling gas too diffuse for our telescopes to detect. What makes the Fornax Void invaluable to astronomers isn't just its mystery, it's a testing ground for our theories of cosmic structure. Smaller voids like this could hold clues about how the universe transitions from dense clusters to empty expanses, a process we've barely begun to map. Future radio telescopes like the Square Kilometre Array might finally reveal the invisible threads tying this void's galaxies together. Until then, Fornax stands as a quiet challenge, proving that even the emptiest corners of space still have stories to tell. We think of the universe as infinite, but the portion we can observe, the Hubble volume has a hard boundary, a frontier set by the speed of light itself. Picture standing on a shoreline where the horizon curves just beyond reach. No matter how far you wade into the ocean, new horizons always lie ahead. That's the paradox of our cosmic view. The observable universe stretches roughly 93 billion light-years across, yet it represents only a tiny fraction of what might actually exist. Beyond this edge, galaxies race away from us faster than light can traverse the expanding space between us, rendering them forever invisible. What makes this limit so haunting is how it warps our understanding of reality. Even if we built a spacecraft capable of light-speed travel, we'd never catch up to those fleeing galaxies. Space itself is stretching, carrying them away like leaves on a rushing river. This isn't science fiction, it's the consequence of dark energy's relentless push, accelerating the universe's expansion so dramatically that distant regions will one day vanish from our view entirely. Already, light from the farthest galaxies we detect arrives stretched and dimmed, their stars' final signals reaching us as faint whispers across billions of years. But here's what keeps cosmologists awake at night. What lies beyond the Hubble volume? One possibility is more of the same, an endless expanse of galaxies, black holes, and cosmic webs stretching into infinity. Yet some theories suggest the unseeable regions could be radically different. Quantum fluctuations during the Big Bang might have sculpted alternate physics in those distant realms, creating pockets where gravity behaves strangely or time flows unevenly. There's even a spine-tingling hypothesis that our observable universe is just one bubble in a frothy multiverse, with other universes lurking beyond the Hubble horizon, each with their own laws of nature. The real frustration is that we may never know. Light from those regions will never reach us, leaving their mysteries locked away. But there's a glimmer of hope in the cosmic microwave background, the afterglow of the Big Bang. Its subtle patterns might encode hints of what lies past our observational limit, like echoes from a distant shore. Until then, the edge of the Hubble volume remains the ultimate cosmic tease, a reminder that the universe's greatest secrets may forever lie just out of sight. Imagine if the universe played a cosmic magic trick, building entire galaxies on a framework we can't see. That's the enigma of dark matter halos, vast, invisible cocoons of mysterious material that surround galaxies like ghostly fingerprints. Without these halos, stars would fly apart, galactic arms would unravel, and the universe as we know it wouldn't exist. Yet despite making up 85% of all matter in the cosmos, dark matter refuses to reveal itself directly. It doesn't emit, absorb, or reflect light. It only whispers its presence through gravity, warping space-time and tugging at the visible universe like a puppeteer hidden behind the curtain. Scientists first stumbled onto dark matter's existence in the 1930s, when astronomer Fritz Zwicky noticed galaxies in the Coma cluster moved too fast to be held together by visible matter alone. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars at the edges orbited just as quickly as those near the center, defying Newton's laws unless some unseen mass was anchoring them. Today, we map these halos by watching how they bend light from distant galaxies, an effect called gravitational lensing, or by tracking the bizarre orbits of stars and gas clouds at the fringes of galaxies. The results are staggering. A typical spiral galaxy like the Milky Way is nestled inside a halo stretching 10 times wider than its visible disk, containing 30 times more mass than all its stars, gas, and dust combined. But what is dark matter made of? The leading candidate, weakly interacting massive particles, or WIMP, hypothesizes an unknown subatomic particle that barely interacts with normal matter except through gravity. Giant detectors buried deep underground, like the LUX Zeppelin experiment, hunt for the rare moment a WIMP might bump into an atomic nucleus. Yet after decades of searching, these elusive particles remain undiscovered. That's led to radical alternatives. Could dark matter be made of primordial black holes, forged in the chaos of the Big Bang? or actions, hypothetical particles so light they behave more like waves than matter. Some theorists even suggest we've misread gravity entirely, that dark matter doesn't exist and our equations just need rewriting. The most tantalizing clues come from galaxies that defy expectations. Take Dragonfly 44, a dim, wispy galaxy with virtually no stars yet the mass of 1 trillion suns, almost entirely dark matter. Or the recent discovery of galaxies seemingly lacking halos altogether, flying in the face of decades of models. These outliers hint that dark matter might be more complex than we imagined, perhaps interacting with itself through unknown forces or clustering in unpredictable ways. What's clear is that dark matter halos aren't just passive scaffolds, they're dynamic players in cosmic evolution. Simulations show how these halos act as gravitational traps, funneling gas into galaxies and sparking star formation. They might even dictate a galaxy's shape. Halos with turbulent histories tend to host elliptical galaxies, while calm ones birth spirals like our Milky Way. As next-generation telescopes like the Vera-C, Rubin Observatory come online, we're poised to peel back more layers of this mystery. Every flicker of bent light, every oddball galaxy brings us closer to answering the ultimate question: what invisible hands sculpted the universe we see today? Beyond the last planets and past even the icy reaches of the Kuiper Belt lies one of our solar system's greatest mysteries, the Oort cloud. This vast, shell-like swarm of icy fragments stretches nearly a light year from the Sun, a frozen graveyard of primordial material left over from the solar system's birth. But here's the catch: no one has ever seen it directly. The Oort cloud exists only in theory, a ghostly frontier inferred from the trails of long-period comets that occasionally streak into the inner solar system like cosmic messengers from the void. The problem with proving its existence boils down to scale. Imagine trying to spot a snowflake in a blizzard from 10 miles away in the dark. The Oort cloud's chunks of ice and rock are spread so thinly that even the most powerful telescopes see only blackness where we suspect they lurk. Yet their influence is undeniable. When a comet like Hale-Bopp or Hyakutake swings into view with an orbit lasting thousands of years, astronomers trace its path backward and consistently find these icy wanderers originate from the same distant region. That can't be coincidence. The Oort cloud acts like a gravitational sponge, soaking up debris flung outward by the young solar system's chaos and holding it in a loose grip until passing stars or galactic tides nudge pieces sunward. But what's truly fascinating is how much we don't know. Some models suggest the cloud isn't a uniform shell but a lopsided structure, warped by the Milky Way's tidal forces over billions of years. Others propose it's not entirely homegrown, that interstellar objects like Oumuamua might actually be captured Oort cloud interlopers from other stars. Then there's the controversy over its mass. Early estimates suggested it could hold several Earths' worth of material, but newer simulations hint it might be far lighter, with comets representing rare exceptions rather than common inhabitants. The Oort cloud's most tantalizing secret: it could be a frozen time capsule. Unlike asteroids or Kuiper Belt objects, its icy bodies have remained untouched by solar heat or collisions since the solar system's infancy. A single mission to retrieve a pristine Oort cloud comet, though technologically daunting, might reveal the original chemical ingredients that birthed our planets. For now, it remains a frontier defined more by its absence than its presence, a reminder that some of the universe's greatest discoveries still hover just beyond our reach. In the vast emptiness between planets, two robotic explorers sent shockwaves through the scientific community without ever realizing it. The Pioneer 10 and 11 probes, launched in the early 1970s to study Jupiter and Saturn, became famous for an entirely unintended reason: their baffling slowdown. As they hurtled toward the edge of our solar system, navigators noticed something impossible. The probes were decelerating slightly faster than physics predicted, as if space itself were dragging on them. This tiny discrepancy, just 9 trillionths of a meter per second squared, became known as the Pioneer Anomaly, a gravitational puzzle that defied explanation for decades. At first, scientists suspected mundane causes, perhaps leaked fuel or electrical glitches. But as years passed and other distant spacecraft showed no similar behavior, the anomaly grew more perplexing. The deceleration persisted with eerie consistency, regardless of the probe's distance or orientation. Some theorized it might reveal flaws in our understanding of gravity itself, hinting at modifications to Einstein's theory of relativity. Others proposed exotic explanations, like the influence of unseen dark matter halos or even higher dimensions warping spacetime at solar system scales. The most tantalizing and controversial idea, that we'd stumbled upon evidence of new physics, a force or interaction beyond the known 4 fundamental forces of nature. Then came the thermal hypothesis. In 2012, a team analyzing decades of Pioneer telemetry noticed a critical detail. The probe's radioactive power sources emitted heat unevenly. As this heat radiated off the spacecraft surfaces, it could create a minuscule but constant push like a car slowing when its driver taps the brakes. Meticulous calculations showed this effect might explain most of the anomaly. Case closed, not quite. While thermal radiation accounts for much of the deceleration, some researchers argue it doesn't fully resolve the discrepancy. The Pioneer probe's metal bodies absorbed and re-radiated heat in complex patterns, leaving room for lingering doubts. What makes this mystery endure isn't just the numbers, it's what it reveals about how science wrestles with the unknown. For 30 years, the anomaly haunted textbooks as a potential crack in our cosmic models. Its near resolution showcases both the power of perseverance and the humbling truth that sometimes the universe's subtlest whispers hold the loudest lessons. Even now, as new missions like New Horizons streak through the outer solar system, astronomers watch for any hint of recurring anomalies, knowing that the next Pioneer-like surprise could be hiding in plain sight. The cosmic microwave background should look like a nearly uniform tapestry, a fading echo of the Big Bang's heat imprinted across the sky. But one patch refuses to play by the rules. The CMB cold spot, a frigid region in the constellation Eridanus, chills astronomers not just with its temperature but with its defiance of probability. This sprawling anomaly stretches over 1 billion light-years, registering a temperature drop so extreme that standard models give it just a 0.0003% chance of existing naturally. It's like finding a single snowflake in a desert, except that snowflake is the size of a mountain. When scientists first mapped this cold spot in 2004, they assumed it must be an illusion, an artifact of instrument noise or data processing glitches. But as new telescopes like the Planck satellite scrutinized it, the anomaly stubbornly persisted. The leading explanation points to a supervoid, an enormous underdense region where fewer galaxies mean less gravitational pull, causing light passing through to lose energy and appear cooler. But there's a catch. The void required to explain the cold spot would need to be so vast and empty it strains credulity, larger than any known structure in the universe. Even if such a void existed, simulations suggest it would only account for half the observed temperature drop. This gap between theory and observation has sparked radical alternatives. One of the most mind-bending proposals suggests the cold spot could be a bruise from a collision with another universe. According to multiverse theories, our cosmos might be one bubble in a frothing sea of universes, each with different physical laws. If another bubble grazed ours during the early universe's inflation phase, the energy release could have left a detectable imprint, a cosmic fingerprint. While this idea remains speculative, it's mathematically plausible within certain string theory frameworks. Skeptics counter that the cold spot might simply be a statistical fluke, an outlier in the CMB's random fluctuations. Yet even they admit its scale is unnervingly extreme. Another tantalizing possibility involves quantum entanglement operating across cosmic distances. In the early universe, particles could have been entangled on scales we now perceive as the cold spot's expanse. If these quantum links somehow suppressed energy fluctuations in this region, they might have created a persistent temperature dip. It's a long shot. Quantum effects usually vanish at macroscopic scales, but some theorists argue the universe's infancy might have permitted exceptions. What makes the cold spot so compelling is how it forces us to question not just our maps of the cosmos, but the tools we use to read them. Could unknown systematic errors lurk in our CMB measurements? Or does this anomaly hint at physics beyond our current grasp, a shadow of forces or dimensions we've yet to discover? Future sky surveys, especially those mapping galaxy distributions in 3 dimensions, may finally settle the debate. Until then, the cold spot remains a frozen enigma, a whisper from the universe's first moments that we're still struggling to decode. Threading silently between the stars like invisible rivers of force, galactic magnetic fields remain one of the least understood yet most influential features of the cosmos. Picture this: vast tendrils of magnetism, some stretching tens of thousands of light years, wrapping around galaxies like cosmic spiderwebs. They're strong enough to guide the birth of stars, shape interstellar clouds, and even funnel cosmic rays, yet so elusive that astronomers only detect them by the faintest imprints they leave on passing light. Take our own Milky Way as an example. Its magnetic field isn't a simple north-south bar magnet but a chaotic tangle, with field lines twisting like stirred spaghetti. Near the galactic center, they're compressed into fierce knots, amplifying the energy of charged particles. Farther out in the spiral arms, the fields act like cosmic traffic cops, aligning dust grains and channeling gas into denser pockets where stars can ignite. But here's the puzzle: where did these fields come from? One theory traces their origins to the early universe, when slight imbalances in the primordial plasma could have sparked weak magnetic seeds. Over billions of years, the churning motion of galaxies, stars orbiting, gas clouds colliding might have amplified these seeds into the sprawling networks we see today. Yet some observations throw this tidy explanation into doubt. Dwarf galaxies, despite their small size and slower internal motions, often host magnetic fields just as strong as those in grand spirals. Even stranger, galaxies in the young universe, barely a billion years old, show evidence of surprisingly developed fields. This has led to a radical alternative. Perhaps magnetic fields didn't grow gradually, but were jumps started by violent events like supernova explosions or jets from supermassive black holes. Imagine tossing a handful of magnets into a whirlpool. Their combined chaos could create order faster than we ever expected. The real magic happens in stellar nurseries. Magnetic fields don't just passively shape star formation, they actively regulate it. In the Orion Nebula, for instance, field lines act like cosmic bungee cords, slowing the collapse of gas clouds to prevent premature star birth. Without this magnetic braking, galaxies might exhaust their star-forming fuel too quickly, leaving them barren and faint. But the fields can also accelerate creation. When oppositely directed field lines reconnect, they unleash torrents of energy, triggering shockwaves that compress gas into new stars. It's a delicate balance. Too much magnetism stifles star birth, too little lets it run wild. What fascinates scientists most is how these fields defy our expectations at every turn. In galaxy clusters, magnetic fields stretch across millions of light years, linking galaxies like beads on an invisible string. Some spiral galaxies show fields perfectly aligned with their arms, while others, like the Whirlpool Galaxy, display bizarre hourglass patterns with no clear origin. Then there's the mystery of reversals, regions where the magnetic polarity flips abruptly, as if the galaxy can't decide which way to point its compass. The challenge in studying these forces lies in their ghostly nature. Unlike stars or gas, magnetic fields leave no direct glow. Astronomers must rely on tricks like measuring the polarization of starlight, how much it's twisted as it passes through magnetized dust, or tracing the alignment of radio waves from distant quasars. New tools like the Square Kilometer Array radio telescope promise to revolutionize this field, mapping galactic magnetism in unprecedented detail. Perhaps the most humbling realization is how much these invisible threads influence the universe's grand tapestry. Without galactic magnetic fields, cosmic rays would bombard planets unchecked, star formation would follow entirely different rules, and galaxies themselves might lack their iconic shapes. They're the silent architects of the cosmos, hidden, pervasive, and still full of secrets waiting to be unraveled. For all the mind-bending mysteries of dark matter and dark energy, there's another cosmic puzzle hiding in plain sight: ordinary matter that's simply gone missing. You'd think the atoms making up planets, stars, and even our bodies would be easy to account for, but the universe loves a good game of hide and seek. According to meticulous calculations, about 30 to 40% of the normal matter the baryons were made of has vanished without a trace. It's like meticulously inventorying a warehouse only to discover half the crates are empty, with no record of what they once held. Where could all this missing matter be hiding? The prime suspect is a diffuse, superheated web of gas known as the warm-hot intergalactic medium, or WIM. Picture this: filaments of ionized oxygen and hydrogen threading between galaxies, so thin they'd make the best vacuum on Earth seem dense, yet so vast they could hold the bulk of the universe's unaccounted-for atoms. The challenge: this gas is wickedly hard to detect. It doesn't glow like stars or absorb light neatly like cold interstellar clouds. Instead, it lurks almost invisibly, occasionally betraying its presence by subtly distorting the light of distant quasars or emitting faint X-rays when stirred by galactic collisions. Here's where cosmic detective work gets creative. Astronomers hunt for the WIM by studying absorption lines in the spectra of faraway quasars, those brilliant beacons powered by supermassive black holes. As their light passes through these tenuous filaments, specific wavelengths get absorbed, leaving minuscule dips in the quasar's rainbow-like spectrum. It's like finding fingerprints on a windowpane, revealing an intruder you can't see directly. The problem: these signals are incredibly faint, often drowned out by noise or confused with other cosmic phenomena. Even the most advanced X-ray telescopes like Chandra and XMM Newton have only glimpsed hints of the WIM structure in clusters where the gas is slightly denser. But the plot thickens. Some researchers argue the missing baryons might not all be in the WIM. They could be hiding in other elusive forms. One theory suggests vast reservoirs of cold gas in galactic halos, too diffuse to emit detectable radiation. Another proposes that high-energy processes like supernova explosions have ejected matter into the far reaches of intergalactic space, where it's cooled into an invisible mist. There's even the spine-tingling possibility that some baryons have been converted into exotic particles through interactions we don't yet understand, blurring the line between ordinary and dark matter. The stakes are higher than they seem. Solving this puzzle isn't just about balancing cosmic ledgers, it's about testing our fundamental understanding of how galaxies form and evolve. Baryons are the raw material for stars, planets, and life itself. If we can't track them down, our models of cosmic structure might be missing a critical chapter. Future telescopes like ESA's Athena mission could finally map the WIM in detail, while next-generation spectrographs may tease out its faint fingerprints with unprecedented precision. Until then, the missing baryon problem remains a humbling reminder. Even the ordinary universe has its secrets. We live in a cosmic neighborhood far grander than most realize, a sprawling metropolis of galaxies called the Laniakea supercluster, stretching 500 million light-years across. This vast web of stars, dark matter, and invisible gravitational currents defines our galactic address on the largest scales we can map. But here's the twist: we're not at its center. The Milky Way drifts along its outer suburbs, caught in a slow-motion river of galaxies, all flowing toward a mysterious gravitational focal point known as the Great Attractor. Laniakea, Hawaiian for immeasurable heaven, isn't a static structure but a dynamic network of filaments where galaxies move like leaves caught in a gentle cosmic stream. Astronomers mapped its boundaries not by tracing visible starlight but by tracking the subtle motions of over 100,000 galaxies, revealing how gravity sculpts their paths. At its heart lies the Norma cluster, a dense knot of galaxies whose collective mass bends spacetime like a bowling ball on a trampoline, pulling everything in Laniakea toward it. Yet even this supercluster isn't isolated. Recent studies suggest Laniakea might be just one lobe of an even larger structure, tentatively called the South Pole Wall, which could span over 1 billion light-years. What makes Laniakea's edges so intriguing is how they blur. Unlike a planet with a clear surface or a galaxy with defined spiral arms, superclusters fade into the cosmic web gradually. Their borders are marked by shifting galactic currents, places where the gravitational pull of neighboring superclusters begins to outweigh Laniakea's own. One such frontier lies near the Perseus-Pisces supercluster, where galaxies seem to hesitate, caught between competing tides of gravity. It's as if the universe itself can't decide where one supercluster ends and another begins. Beyond these filamentary edges lies the unknown. Some theories suggest we're part of a hierarchy so vast that superclusters themselves are mere threads in a super-duper cluster. Others propose that Laniakea's outskirts might harbor primordial relics, ancient gas clouds untouched since the Big Bang, or wandering black holes ejected from galactic collisions. Then there's the haunting possibility that we're limited by cosmic horizons. The expansion of space may forever hide whatever lies beyond Laniakea's furthest reaches. The irony is palpable. Even as we define our place in this grand structure, we're reminded how much lies beyond our grasp. Future telescopes may reveal whether Laniakea truly stands alone or is just one cell in an unfathomably larger cosmic organism. Until then, its edges remain a frontier not just of space but of our understanding. Most particles announce their presence with flashes of light or trails of destruction, but not neutrinos. These ghostly subatomic particles slip through entire planets without a whisper, making them nearly impossible to detect. Yet there are places in the universe where even these elusive wanderers grow scarce, regions astronomers call neutrino deserts. Picture vast cosmic voids where particle interactions are so rare that neutrinos, normally passing through matter like sunlight through glass, suddenly find nothing to brush against at all. It's like being the only dancer in an empty ballroom with no partners to twirl. These deserts form in the most extreme environments imaginable, deep in interstellar space far from galaxies, or near the edges of black holes where matter is funneled away into oblivion. Even supernova, normally neutrino factories, can create temporary deserts in their aftermath. When a star explodes, it floods space with neutrinos, but once that initial burst fades, the surrounding area becomes eerily silent. Scientists discovered this by comparing neutrino detections from supernova like SN1 987 with the expected numbers. The discrepancy revealed patches of space where neutrinos seemed to vanish, absorbed or scattered by processes we're still unraveling. The challenge of studying these deserts reveals just how strange neutrino astronomy truly is. Most telescopes rely on light, but neutrino detectors, like ice cube buried in Antarctic ice, wait years just to catch a handful of particles. When a neutrino finally interacts, it creates a faint blue flash called Cherenkov radiation. But in deserts, even those rare flashes dwindle to almost nothing. This creates a paradox. The emptiest regions of space might hold clues to the most violent cosmic events. Neutrinos born in the hearts of collapsing stars or active galactic nuclei travel billions of light-years undisturbed, carrying pristine information about their origins if we can catch them. Yet these deserts aren't just astronomical curiosities, they're cosmic pressure gauges. The density of neutrinos in a region reflects the universe's underlying structure, tracing the invisible scaffolding of dark matter. Some theories even suggest neutrinos themselves could decay into yet undiscovered particles in these sparse zones, leaving behind ghostlier remnants. Future detectors, like the proposed Pacific Ocean neutrino experiment, might finally map these voids in detail, turning absence into discovery. What makes neutrino deserts so mesmerizing is how they invert our expectations. In a universe teeming with particles, emptiness becomes the anomaly, a silent symphony where the missing notes hold the deepest secrets. As we push the boundaries of detection, these barren patches remind us that sometimes the cosmos speaks loudest in its quietest corners. Zoom in far enough, past atoms, past particles, even past the tiniest quarks, and spacetime itself might not be the smooth fabric we imagine. At scales a million billion times smaller than an atom, the universe could be a seething, frothing ocean of chaos known as quantum foam. Picture an endless storm where space and time bubble and warp, popping in and out of existence so fast that the very concepts of here and now lose all meaning. This isn't just theoretical whimsy, it's a frontier where Einstein's relativity and quantum mechanics collide, revealing a reality far stranger than either theory alone could predict. The idea of quantum foam springs from a simple but mind-bending principle: uncertainty. At these infinitesimal scales, the energy of the vacuum isn't calm and empty, but a roiling frenzy of virtual particles, pairs of matter and antimatter that flicker into existence for fleeting instants before annihilating each other. These fluctuations aren't just happening in space-time, they are space-time, twisting it into a probabilistic labyrinth where distances and durations blur. Imagine trying to measure the surface of a boiling pot of water with a ruler. The closer you look, the more the bubbles distort your measurements. That's the challenge physicists face when probing Planck scales, the universe's ultimate resolution limit. Black holes offer a tantalizing glimpse into this quantum chaos. Near a singularity where gravity crushes matter beyond recognition, spacetime's foam-like nature might become dominant. Some theories suggest that instead of collapsing into an infinitely dense point, a black hole's core could dissolve into a knot of quantum foam, a place where cause and effect tangle and space loses all orientation. This could explain why nothing, not even information, escapes a black hole's grip, not because it's trapped, but because the very structure of reality breaks down into something we can't yet describe. The cruel irony: we may never observe quantum foam directly. The Planck length, the scale at which this turbulence dominates, is so absurdly tiny that probing it would require energies a quadrillion times greater than what the Large Hadron Collider can produce. It's like trying to hear a whisper in a hurricane. The tools we'd need to detect such fine-grained chaos would themselves be obliterated by the energies required. Even nature seems to enforce this limit. The shorter the timescale you examine, the more energy you need, until you're essentially creating microscopic black holes that shut down the experiment. Yet the foam's ghostly influence might still be detectable indirectly. Some models predict that over cosmic distances, the cumulative effect of spacetime's turbulence could subtly alter the paths of high-energy photons or neutrinos, leaving faint fingerprints in the light from distant quasars or gamma-ray bursts. Other theories suggest that if we could measure time with enough precision, say, with atomic clocks accurate to within 1 second over the age of the universe, we might catch spacetime itself jittering at the quantum level. What makes quantum foam so electrifying isn't just its strangeness, but what it implies about the universe's foundations. If spacetime is fundamentally granular, not smooth, it could rewrite our understanding of everything from the Big Bang's first moments to the fate of information in black holes. It's a reminder that the cosmos doesn't owe us intuitive answers sometimes. The deepest truths are hidden in the storm beneath the surface, where reality itself is constantly rewriting the rules. While black holes devour everything in their path, their theoretical opposites, white holes, spit matter out with unstoppable force. Picture a cosmic fire hose blasting energy and particles into the universe, utterly refusing to let anything back in. These hypothetical objects emerge from the same equations that predict black holes, essentially playing the footage of gravitational collapse in reverse. But here's the catch: despite decades of searching, not a single white hole has ever been observed. Are they mathematical curiosities, or could they hide in plain sight, disguised as other cosmic phenomena? The concept springs from Einstein's theory of general relativity, which treats time as flexible. Just as a black hole's event horizon marks a point of no return for infalling matter, a white hole's horizon would be an exit door nothing can re-enter. Some theorists suggest white holes could be the other end of black holes, connected through an Einstein-Rosen bridge popularly known as a wormhole. Imagine a black hole in one part of the universe slurping up matter, only for a white hole in another region to spew it out like a cosmic conveyor belt. The problem: wormholes are notoriously unstable, likely collapsing faster than light could traverse them. Another twist comes from quantum mechanics. When black holes evaporate via Hawking radiation, some models suggest their final moments could briefly resemble a white hole's explosive release of energy. This has led to speculative ideas like black hole fireworks, where dying black holes transform into white holes in their last gasps. But the timescales are mind-boggling. A stellar mass black hole would take longer than the current age of the universe to evaporate. By then, the resulting white hole's outburst would be pitifully faint, drowned out by the cosmic microwave background. White holes also flirt with one of physics' biggest taboos: violations of causality. If they exist, they'd essentially be regions where time runs backward relative to our universe. A cup shattering in a black hole might reassemble in a white hole unscathed. While tantalizing, this clashes with the second law of thermodynamics, which dictates that entropy disorder always increases. The universe seems allergic to time-reversed processes, making white holes appear absurdly improbable. Yet some astronomers hunt for their fingerprints. A handful of unusual cosmic explosions, like the bizarrely bright and fast FRB 190523, have sparked debates. Could these be white holes erupting? Others speculate that the Big Bang itself might have been a primordial white hole event, birthing the universe in a single explosive moment. While evidence remains scarce, the search continues, because if white holes exist, they'd rewrite our understanding of time, gravity, and the very fabric of reality. For now, they remain one of cosmology's most tantalizing mirages, a reminder that the universe's extremes might be far stranger than we dare imagine. Somewhere beyond the farthest galaxies, lurking in the equations of quantum field theory, hides an invisible line that could rewrite reality itself: the vacuum metastability event horizon. Picture a cosmic minefield where the very ground beneath our feet isn't solid but balanced on a knife's edge. According to some physicists, our universe might not be in its lowest energy state. It could be a false vacuum, temporarily stable but capable of collapsing into a more fundamental form at any moment. If triggered, this phase transition would race outward at the speed of light, rewriting the laws of physics in its wake and erasing everything we know before we could even see it coming. The math behind this doomsday scenario stems from the Higgs field, the same quantum backdrop that gives particles their mass. Current measurements suggest this field might be metastable, like a marble balanced on a hill rather than resting at the bottom. A strong enough disturbance, say a high-energy particle collision or a quantum fluctuation, could theoretically knock the field into a lower energy state. The result, a bubble of true vacuum, would expand uncontrollably, its walls carrying a new set of physical constants. Atoms would disintegrate, forces would unravel, and the universe as we know it would cease to exist in an instant. Here's the terrifying catch: we wouldn't know the event had begun until it reached us. The transition's boundary, the event horizon, would be completely invisible until it arrived, since the change propagates at light speed. By the time we detected any warning signs, like strange particle behavior or shifts in fundamental constants, it would already be too late. The horizon could emerge just a few light years away, or already be sweeping through distant star systems without our telescopes noticing. Ironically, regions with extreme gravitational fields might offer temporary shelter. Near black holes, spacetime's curvature could theoretically slow the phase transition, creating pockets where the old laws of physics stubbornly persist. It's a haunting thought, civilizations huddled near singularities, clinging to existence as a wave of annihilation closes in from all sides. Yet for all its apocalyptic grandeur, the vacuum metastability event remains highly speculative. Many physicists argue the Higgs field is likely stable, or that the energy required to trigger collapse exceeds anything possible in nature. Others suggest that if such events were probable, they would have already happened somewhere in our cosmic past. But the mere possibility forces us to confront an unsettling truth. The universe's deepest laws might be more fragile than we ever imagined, with unseen boundaries where reality itself could shatter without warning. What if the Big Bang wasn't the beginning, but just the latest chapter in an endless cycle of cosmic collisions? Hidden in the equations of string theory lies a radical alternative to our standard origin story. The ekpyrotic universe, where our entire cosmos exists as a floating membrane, or brain, crashing into another in an event that could rewrite time itself. Picture two sheets of paper drifting through an unseen dimension, slamming together with enough force to spark not just stars and galaxies, but the very fabric of space and time. This isn't science fiction, it's a serious hypothesis that swaps the singularity of the Big Bang for something even stranger, a rebirth born from collision. The ekpyrotic model turns conventional cosmology on its head. Instead of an infinitely dense point exploding into existence, it proposes that our universe is one of many three-dimensional brains drifting through a higher dimensional bulk. When these brains collide, drawn together by invisible forces, the impact unleashes enough energy to mimic a Big Bang, scattering matter and radiation across the reborn brain. The aftermath would look identical to our observed universe, complete with cosmic microwave background and expanding galaxies, but with one crucial difference: no singularity at time zero. Time could stretch infinitely backward before the collision, sidestepping the need for a definitive beginning. But here's where the theory gets truly mind-bending. The ekpyrotic scenario could solve one of cosmology's biggest headaches, the flatness problem. Our universe's spacetime is improbably flat, with matter and energy balanced perfectly against expansion. Traditional inflation theory explains this by proposing a rapid exponential growth spurt in the universe's first moments. The ekpyrotic model offers an alternative. The slow, grinding approach of two brains before collision would naturally smooth out wrinkles, leaving spacetime flat without requiring an inflationary period. It's like rolling out dough between two boards. The pressure creates an even surface before the final cosmic bake-off. Evidence for this invisible brain dance remains elusive, but tantalizing clues might hide in gravitational waves. Unlike the abrupt burst of inflation's gravitational ripples, an ekpyrotic collision would produce a subtler signal, a background hum of low-frequency waves woven through spacetime. Future detectors like the Laser Interferometer Space Antenna could potentially pick up this whisper from the pre-collision era. There's also the controversial cold spot in the cosmic microwave background. Some theorists argue its unusual properties align with brain collision scars, though skeptics counter that statistical flukes can't be ruled out. The implications ripple beyond mere geometry. If our universe is a brain, others might float millimeters away in higher dimensions, forever invisible because gravity alone can traverse the bulk. Dark matter could be matter from a neighboring brain, its gravity leaking through while its light stays trapped, and the cycle continues. After expansion, our brain might eventually snap back, drawn toward another cataclysmic rendezvous. No heat death, no big crunch, just an endless cosmic heartbeat of collisions and rebirths. What makes the ekpyrotic universe so compelling isn't just its audacity, but its refusal to let cosmology rest on a single moment of creation. By trading the Big Bang's fireworks for a quieter, cyclical reset, it offers a vision of time without edges, a universe that may have always been, and always will be, dancing in the dark with partners we can't yet see. What if everything you see, the stars, the planets, even your own hands, isn't truly three-dimensional but an incredibly convincing illusion? The holographic principle suggests exactly that. Our universe, with all its sprawling galaxies and intricate quantum fields, might be nothing more than a two-dimensional projection playing out on some unimaginably distant cosmic boundary. It's as if reality is a cosmic IMAX screen, and we're just the shadows dancing across its surface. This radical idea didn't come from science fiction but from studying black holes. When physicists calculated how information behaves at a black hole's event horizon, they stumbled upon something startling: the maximum entropy, or chaos. A region of space can hold doesn't scale with its volume but with its surface area. In other words, all the data needed to describe what's inside a black hole could be perfectly encoded on its outer shell. Extend this logic to the universe itself, and you're left with a dizzying possibility. Our 3D reality could be a holographic projection from a flat, two-dimensional surface at the edge of everything we know. But here's where it gets even stranger. If the universe is a hologram, what's projecting it? Imagine standing in front of a movie theater screen. You see the images, but the real magic happens in the projector's hidden machinery. In this cosmic analogy, the projector would exist beyond the boundary of our observable universe, in a realm we can't see or interact with. Some theories suggest this boundary could be the cosmic event horizon, the point where space expands faster than light can travel, forever cutting off any view of what lies beyond. Others propose it's a mathematical construct, a surface where quantum bits of information flicker like pixels, weaving the fabric of our reality. The implications are staggering. If the holographic principle is true, then free will, time, even our sense of self could be emergent phenomena, illusions generated by the interplay of data on that distant screen. It's like realizing the characters in a video game aren't making choices at all. They're just following code written somewhere else. This raises a haunting question. If we're projections, what or who is the coder? Some physicists speculate it could be a deeper layer of reality, perhaps a higher dimensional universe where our screen is just one of many. Others argue the question might be meaningless, like a character in a novel asking who's holding the pen that writes their story. Yet for all its abstraction, the holographic principle isn't just philosophy, it's testable. Scientists have looked for evidence in the cosmic microwave background, searching for telltale patterns that might reveal pixel-like structures in spacetime. So far, the results are inconclusive, but the hunt isn't over. Future experiments probing quantum gravity or the nature of entanglement might uncover fingerprints of this cosmic encoding. What's most humbling is how this idea inverts our intuition about reality. We think we're the solid, tangible stuff of the universe, but we might just be fleeting patterns on the surface of something far more profound. The holographic principle doesn't just shrink the universe, it collapses dimensions, turning the vast cosmos into a shadow play on the ultimate boundary of existence. And somewhere beyond that boundary, in the unseen machinery of reality, the true nature of the projector remains one of physics' greatest unanswered riddles. What if everything we perceive, the stars, planets, and even our own thoughts, isn't the foundation of reality but lines of code in an unfathomably advanced simulation? The idea that our universe might be artificial isn't just sci-fi fodder. It's a serious hypothesis debated by physicists and philosophers alike. Proponents point to eerie glitches in the fabric of reality that resemble programming quirks, particles that behave differently when observed, mathematical constants fine-tuned to impossible precision, and quantum entanglements instant communication across vast distances, like a processor optimizing render distance in a video game. Take the double-slit experiment where particles act as waves until measured, then suddenly collapse into definite states. This isn't just strange, it's suspiciously efficient, as if the simulation conserves processing power by only calculating outcomes when necessary. Then there's the universe's pixel-like limit, Planck length and time, the smallest measurable units beyond which reality becomes fuzzy. Could these be the resolution limits of whatever system is running our cosmic program? Even déjà vu and Mandela effects, those unsettling moments when collective memories don't match documented history, have been jokingly or seriously framed as memory buffer errors or patches rolled out mid-experience. But the most haunting clue might be the universe's mathematical perfection. From the Fibonacci sequence in sunflower spirals to the gravitational equations governing galaxies, nature follows rules that feel less discovered than written. Nobel laureate George Smoot once quipped that the precision of cosmic laws made it seem like a programmer got lazy and reused the same code everywhere. Some theorists argue this isn't coincidence but evidence of an underlying architecture, an operating system with elegant, reusable functions. Yet if we're living in a simulation, why can't we find the source code? The answer might lie in the very rules of the simulation itself. Just as a video game character can't access its programming files, we could be bound by the simulation's parameters, forever locked out of the higher reality. Firewalls might exist to prevent players from crashing the system, explaining why particle accelerators hit energy limits or why black holes erase information. Some physicists suggest attempting to hack the system by probing for computational shortcuts, like searching for rounding errors in cosmic constants or lag in quantum measurements. The simulation hypothesis forces us to confront existential questions. If our universe is programmed, who or what is the programmer? Are we NPCs in an alien civilization's ancestor simulation, or are we the AI, evolving towards self-awareness within the simulation's rules? And if reality is code, does that make consciousness a subroutine or the ultimate bug? Until we uncover irrefutable evidence or the system admin responds to a cosmic help ticket, the simulation remains the ultimate cosmic mystery, a universe that might just be someone else's science project. From the Great Attractor's invisible pull to the quantum foam's subatomic storm, these 25 enigmatic regions remind us how much of the universe remains shrouded in mystery. They challenge everything we think we know about gravity, about time, even about the nature of reality itself. Each one is a cosmic puzzle piece, revealing just enough to tantalize us while guarding its deepest secrets. Whether it's the Fermi Bubbles' ghostly glow or the Oort cloud's silent frontier, these are places where the universe whispers its unfinished story, daring us to listen. But here's the beautiful paradox: every unanswered question is an invitation. For all our telescopes and equations, the cosmos thrives on wonder, on the spaces between what we've mapped and what we've yet to imagine. Think of the astronomers who first spotted the CMB cold spot, or the theorists wrestling with dark matter's grip. Each discovery, each dead end, is part of humanity's grand conversation with the universe. It's a dialogue that spans centuries, from Galileo's telescope to the James Webb's infrared gaze, and it's far from over. So tell us, which of these cosmic mysteries keeps you awake at night? Is it the eerie emptiness of the Boötes Void, or the unsettling precision of the holographic universe? Drop your thoughts in the comments, and let's keep the curiosity alive. And if you're hungry for more deep dives into the cosmos' greatest enigmas, hit that subscribe button. The universe isn't done surprising us, and neither are we. Until next time, keep looking up, because out there, in the dark between the stars, the next great mystery is waiting.